Hello scholars, welcome back. Mr. Hinkle, and we're talking about the way that our Earth spheres, the biosphere, the hydrosphere, the atmosphere, the cryosphere, the exosphere, oh, there's one more, the geosphere, yes. How do they interact? Well, they interact through specific ways, and we call these ways events and interactions, most specifically forcings, feedbacks, sinks, and tipping points. And so I love this image here because it's showing the water cycle. The water cycle that is hanging out in the ocean, is hanging out in the atmosphere, it's moving through the rocks, it's going through the ground. At some point, the ice and the snow are going to melt. So the way that water interacts with rock and air is going to be through, well, interactions and events. And these are the very specific ones: forcings, feedbacks, sinks, and tipping points. So a forcing event is an action that happens on Earth that moves a system away from its equilibrium state, from a point where it would not change. So examples of this could be warm temperatures melting ice. It could be a volcanic eruption. It could be more aerosols in the atmosphere. So when a forcing event happens, we get feedbacks. And feedbacks go like this. They can be positive or negative. Positive feedback is in the direction, the response is in the direction of the stimulus. Negative feedback is going to be in the opposite direction. So for a negative, we could say, I'm cold. I'm cold. So what do? I put on my jacket. And then I get warm again, right? Gotcha. Now, I'm not cold anymore. Or I'm hot. What do? I take off my jacket, and then I'm not hot anymore. Now, a positive feedback is like a snowball, right? And so here's a great example of a positive feedback. Glaciers melt, and the temperature rises, right? So the atmosphere gets hot. What happens? Glaciers melt. When the glaciers melt, there's less ice cover to reflect the sun, which means that temperatures get hotter. Temperatures are hot, more glaciers melt. More glaciers melt, the temperature gets hotter. So on and so forth. So the response is in the direction of the stimulus, where for a negative feedback, the response is in the opposite direction. I'm cold and I get warm. Let's use a volcanic eruption. So the event, the volcanic eruption, affects the lithosphere. It blows rock and ash off of the mountain, distributing it to wherever it goes. We might have new rock forming from a lava flow. A pyroclastic flow might run down the side of the slope. If that mixes with snow, ice, or water, it'll create a lahar, a wet flurry of mud and ash and dust that can be very destructive, killing and wiping out all life that might be in its path and ejecting particulates into the atmosphere. There's a few big earthquakes, yeah, I mean, they shook the earth, granted, but big volcanoes. Krakatoa, back in the 1860s, erupted. Mount Tambora, early on in the 19th century, erupted. And they ejected so much ash into the atmosphere that it actually caused seasons of global cooling because it was upsetting the energy budget. Yeah, Earth Systems Through Time, energy, we got it? Yeah, great. It upset the energy budget and blocked some incoming solar radiation. So the forcing event has feedbacks in all of Earth's spheres. Wow, that really rolls off the tongue, doesn't it, right? So the FE creates feedbacks FB through Earth's spheres, ES. Some things just roll off the tongue. Okay, what do we got? A viral pandemic. That's a forcing event. We were all forced to stay home. There was a lot of events there. Burning of fossil fuels leading to climate change, earthquakes, asteroid impacts, deforestation. This is why it's not good to cut down all the trees. See Easter Island. Supervolcano eruption, stratovolcano eruption, and then the melting of polar ice. So, for example, I put these in here for you to look at the forcing event and the effects in the lithosphere, the hydrosphere, the atmosphere, the biosphere, because events don't happen in isolation. They affect all of the Earth's spheres. They affect the Earth system. Sinks. So when a forcing event happens, where does the matter and energy go? It goes into a sink until it can be moved to the next location. Carbon is really, I think it's the best way to think about this. So we have mountains in the ocean, carbon dioxide in the atmosphere, gets absorbed into the oceans and used by marine life to produce their shells, and accumulates at the bottom of the ocean to make carbonate rock. That carbonate rock, slowly over time, plate tectonics, makes its way into a subduction zone where it will travel back up to erupt in the atmosphere and feed more carbon dioxide into the atmosphere. So what are the sinks for carbon in the biogeochemical cycle of carbon dioxide? The atmosphere, the hydrosphere, the lithosphere, the geosphere. In the organisms, the biosphere, literally in all of them. And then it makes its way back up into the atmosphere. Hooray! Okay, now energy and matter can store in sinks, but they can also reach a point of no return. And so we return, not to the point of no return, but we do return to the positive feedback of melting glaciers. This is happening. Climate's warming, glaciers are melting, but it hasn't caused major disruptions. Right now, the Gulf Stream and the AMOC, which transport a lot of heat from equatorial regions all the way up to Europe, Northern Europe, is being influenced by the amount of melting ice in Greenland. And at some point, the caution is, if too much of Greenland's ice melts, it disrupts oceanic circulation, thereby shutting down the global circulation of ocean waters, thermohaline circulation. And if that happens, that would be bad, because that is how we redistribute heat across Earth's globe. So melting ice could lead to a major disruption in ocean circulation if and when a tipping point is reached. So what do we do? What do we do? Just sit here and throw our hands up and go, there's nothing we can do here. Rabble, rabble, rabble. Well, we make diagrams, causal loop diagrams. So we try and map out the connections and the forcing events and the feedbacks, the sinks, and the tipping points in order to get an understanding of what these interactions between Earth's spheres are, which ones we need to be tuned into. Melting ice, this is a big issue currently because the Earth is warming and ice is melting. And what is going to happen? Well, we can look at these causal loop diagrams, trying to understand the interactions in as many directions as possible to help us focus where we need to set our attention to study and to learn to help better understand our Earth system, and also to make good decisions about how we manage our Earth system. So The Earth has spheres. They interact with each other through forcing events, feedbacks, sinks, and tipping points, and we can observe them through causal diagrams. Thank you so much. I'll see you again.